Computed tomography.
Computer tomography, industrial computer tomography.
Fancy word.
You can read it right off the screen.
That's cheating.
We might be waiting a few seconds here. You want to just let everybody know that we're waiting just for a moment?
We're waiting for if any more people come in the room for a few more seconds here. Okay. Good morning again. This is the track A on Thursday, which is mostly product tutorials. Right now we have Bob and Jackie from Werth, and they're going to be talking about their computed tomography equipment. Thanks.
Good morning, and thank you for stopping by and this opportunity to be able to explain a little bit not only about our products, but about what computed tomography actually is. Jacqueline's going to start off. My name is Bob, and hopefully it'll be a presentation that'll provide some insight into computed tomography.
Hi, so I'm going to start with a photograph of our headquarters. Werth is located in Germany, roughly an hour north of Frankfurt, and we do almost everything at this facility from research and development to product assembly to our European sales team being based out of this office. So Werth was founded more than 60 years ago. We have roughly 11,000 machines around the world, and I just want to highlight our specifications. We operate according to ISO 9001, VDE, VDI 2617, and ISO 10360. And we have several lines of products. In addition to our line of CT machines, we have a line of shop floor machines, a line of lab machines, and then we have our CT machines. All of our measuring machines have an MPE from 5 microns down to 150 nanometers, and we also offer a wide range of product sizes that we can measure. Oops. And this is our line of tomoscopes. We recently came out with the Tomoscope XS in the upper left corner, but we have several other models, and we can recommend to you the one that you would need based on material density and part size. And these are certifications ISO 9001, and this DOC certification allows us to calibrate our own artifacts. DOCS is the German equivalent of NICE. And this is our ISO 17025 certification. And all of our CT machines meet FDA requirements to be considered a cabinet X-ray machine. There is no additional PPE necessary. Our CT machines are built to be a CMM with an X-ray sensor on it. It has temperature compensation, pre-calibrated magnifications, an accuracy of 2 to 10 microns, and we also sub-voxel, which is something that I will get into later on in the presentation. So the basic principles of CT is you have your X-ray source on one side, your part rotating 360 degrees in the center, and your detector on the other side. Werth uses transmission target tubes. This is important because a lot of other companies use reflective target tubes. So when the electrons hit the target, they form and they bounce off into a X-ray cone, and with the reflective tubes, that bouncing off of the target does not allow you to get as tight of a focus spot as with the transmission target tubes, where the X-rays are transmitted through the target. A micro focus spot is important because your voxel size should not be smaller than your focal spot size. Your voxel size is your volumetric pixels, and that determines resolution and also affects accuracy. And this chart shows that relationship between power and focal spot size. So the blue line would be your transmission target tubes, and the red would be your reflective tubes. So as you can see, you can increase the power on the transmission target tubes without significantly increasing the focal spot size. And then this shows you the effect of your focal spot size on your resolution. So here we have a larger focal spot. The X-ray beams are going in different directions, and that creates a shadowing effect on your part. The image on the left is a live image of what you would be seeing. And as you tighten that focal spot size, you're getting a clear image of your part.
The one thing about computer tomography and X-ray machines is that this is nothing more than a very, very fancy camera. You can only compensate for certain amount of overexposure, if you want to call it that. So it's cone beam tomography. All tomography machines work on a cone beam. There are linear arrays, which that would be in a perfect world, be a great way to take a picture in straight. And you get your best focal, less deflection of the photons going through the part straight on. But that would take a very, very long time to X-ray anything. So we use a cone beam. And as you can see, it's like a flashlight, putting a flashlight up, and you get a little bit of a nice tight spot right in the middle where you want to shine, and then over to the sides, you get the cone beam artifact. You get a little bit of a blurriness off to the side. This is a nice tight focal spot. Can you go backwards for me, please? And then with a wider focal spot, your actual live image, you can't compensate. There's no algorithm, because you need to be able to reconstruct this pixel picture and reconstruct it into a voxel volume. Having a blurriness, when you start out with a blurry picture, you can't reconstruct it into a nice tight picture.
So in CT, there is no precision fixturing necessary as long as your fixture has a lesser density than your part. So for plastics, we like to use a styrofoam that's very low density. In terms of magnification, it's almost like in a movie theater. So the closer your hand is to the projector, the larger it will be on the screen. The closer your hand is to the screen, the smaller your hand will be. And all of our detectors have a scintillator coating, so that converts X-ray radiation into visible light, and then your photodiode will convert that physical light into a digital amplitude. So within the software, you can also adjust for voltage, current, exposure time, and this will affect the quality of your image. In the bottom, you can see the green boxes. So the software will tell you, is this going to be an ideal image to take a scan? So when that's green, you're good to go, and red means you need to make some more adjustments.
So the point that you made, you said it's a blurry image. Hello, Derek D. Mason. The question I have, one of the points you had made as far as a blurry image, and I was looking for some type of software adjustment that you use. So does the software clean up the image or anything like that? I mean, what does the software in particular do?
There is virtual artifact correction, empirical artifact correction. Artifacts are a little bit different than an actual focal spot. When the focal spot is taking a little bit of a shadow, that is not an artifact. Artifacts are caused by things like beam hardening, where we'll show you a little bit about beam hardening, or the cone beam, where, like I said, the linear array would be the best place to see a nice right straight in that middle. We do have helical scanning. So you can actually helical scan in an array, put a filter over the X-ray source, just have the straight beams coming out from the X-ray source, and helical scan, do a 360-degree scan as you're scanning and slowly move the part up. It's a very long process because you're only in that. So cone beam effect is a little bit different. Only the middle of the part gets a nice crisp image, but you have to have a small focal spot for that nice crisp image. Artifacts like cone beam effect and beam hardening, yes, there is an algorithm that we've created, and also other people have, but Werth was one of the first companies to come out with autocorrection. So we put a correction curve based upon material, voltage, known facts of the scan process. And it's another algorithm that goes upon other algorithms to do all the reconstructive, but we're able to take out artifacts. But it's like a camera. If your picture is blurry when you're taking it, no matter what kind of software you have to reconstruct it, Photoshop, it's still going to be a blurry picture.
So we are constantly rotating the part, and while we're doing that, we're taking between 1,000 and 2,000 images. Werth has parallel reconstruction, so while you're taking the images, we are overlaying them onto each other to get a total 3D view of your part. And something that Werth has patented is CT on the fly, so we never have to stop the rotary table. A lot of other companies have to accelerate, decelerate, stop, take a picture, and continue that 1,000 times. But we're able to continuously rotate that, which significantly decreases your scan time. What would previously take 20 minutes for a plastic part, we can now reduce that to between 2 and 3 minutes. And then once you have your stack of 2D images, we compress them into your 3D voxel volume. And the color of your part is determined based on density. So totally black would be air. It has no density. And as you can see from this image, the bottle plastic is more dense than the cap plastic. And we also have automatic threshold definition within Werth, so that reduces operator influence. And then from your voxel volume, we take the greatest change in density, but usually between air and your part, and we put a point there. Because they are all points without vectors, we connect each point to its 2 nearest points in a series of interconnected triangles to generate an STL. And that is a smoothed out image of your STL here. How we can do that accurately, so I'm going to take that back into a 2D view. So Werth has our image processing sensor. So this image on the top left is purposely blurry. So each color value has a digital amplitude. So black would be 0 and white would be 250. So we're looking for the greatest change in digital values, and we put a pixel contour there. From there, we're able to subpixel or go into the pixel and interpolate where your point would be. We don't just put the point in the center of the pixel. So that gives you a higher accuracy on your contour.
So going from a pixel or a CCD chip, this is every optical system works the same way. You have a CCD chip, you have within that CCD chip you have pixels, and those pixels might be 50 micron pixel size, a native resolution of 50 micron. So how do you get down to 2 micron? How can you say you can measure to 2 micron if your pixel size is 50 micron? Because you're going to create an image stack or a voxel. Voxels have weight, and each point within inside that voxel, okay, think of it as a cube. Think of it as 3 by 3 by 3, so 27. So you have 27 little points to make up a single point within that point cloud. And that point cloud now needs to have some kind of a coordinate system or a vector put in. That's where the STL comes in. But to be able to move those points within that histogram or that density curve, okay, you have no material, or you have a little less denser material, then you have a dense material, and that's what the histogram's going to show you. So we're able to go within that, just like in a pixel, and move, okay, we have the next closest value to our best fit element is going to be over to the right or over to the left. So you can move the center of gravity of that voxel point, and you move it over a little bit. That gives you a little bit better resolution. Then you have a calibrated pixel size. Like Jackie says, when you move that back and you magnify that picture, you get a calibrated pixel size. So now your pixel size can go down to 15, 10 micron. And then being able to subpixelate can get us to that 2 micron, 1 micron size.
Okay, and like Bob said, we take that 2D concept and we move it into 3D for our voxels. Within the Werth software, you can import your CAD file, and then you have your point cloud that you generated from your scan. Marry the two together with our best fit, and then you're able to get a quick range of where you're in and out of spec. So the greens and blues are in specification, reds and purples are out of spec, so you can quickly see where you need to make adjustments. You're also able to measure 3D geometric elements. So here we are looking at a gas injector nozzle. We chose all of the points that belong to a cylinder, calculated the cylinder, and then you're able to generate that heat map and see that the cylinder barrels out in the middle. You're also able to take 2D measurements. You can do that by creating a plane along any point in the part, and then looking at the features on that plane, measuring lines, distances, radii, all of that. With our voxel sensor, you're also able to look at multi-material parts and measure distances between those as well. You can see voids in the components depending on the size of the void. If it's 5 microns, 2 microns, that's probably not something that you would be able to pick up, just because you need to generate several points around the void to determine if it is actually a void. So you're probably looking at being able to see voids that are 25 microns or larger. In terms of repeatability, we did a study on this part over the course of a week, 20 measurements, all different times of the day. We were looking at 6 things: the diameters of all the balls, and then the distance between their center points to each other. And we got the largest range was 700 nanometers for each measurement.
The total value after a week study, the total value, all ranges, repeatability after 20 was less than 700 nanometers. And that includes form tolerance, includes the distances, includes the balls. When you take, can you go back just quickly to the 2D measurement? I want to expand on the 2D measurement a little bit, because when you create a computer tomography image, you actually create a 3D, it's a true 3D scan. There's no hidden features. It's not taking the outside contours. You're not just looking at the outside of a part or the top and be able to get the tomography of the top of a part like you would on an optical system. You're able to actually go inside, and any place you want to take that STL, you can slice it. So you don't have to slice it straight down the middle. You can take any shape, any place you want, any feature that you want to see. So additive manufacturing, for anybody that does additive manufacturing, this is a great tool for that, because you can design things in additive manufacturing. You can do all sorts of interior channels and shapes that It's no more drill and plug and then go down the other side. You can do anything you want, but you still need to measure that. You still need to make sure that those channels, those plugs, you know, those holes, all those are measured, are in the right place and the right dimensions. This is a great tool for that. So when you see a quick shape down the middle, I don't want you to think that the only place you can split an STL, or you can fly through the voxel volume.